Today we're going to be reviewing log functions. Okay, this is mostly pre-calculus stuff, but it's something that we probably need to review. Alright, so this we think, if you rewrite this in exponential form, 2 to what power equals 8? And hopefully that you know that is 3. Right, so this log expression should equal 3. Okay, this one, 3 to what power equals 81? Or 1 over 81. So I could flip that over. 3 to what power equals this, and keep going. I can rewrite 81 as 3 to the 4th to the negative 1st, so the question mark here is going to be equal to negative 4. So this logarithmic expression, log base 3 of 1 over 81 equals negative 4. And then this one, 16 to what power equals 4? And this would be 1/2, or square, it's a square root, and we know that's a 1/2 power. Alright, so I'd like us to be able to sketch the graph of log base 4 of x without a calculator, and you can do that by making a table and evaluating the function just like we did on the previous page. Alright, so if I try to figure out if we find 4 to what power equals x, that would be negative 1. Okay, 4 to what power equals 4? That's the first. 4 to what power equals 16? That would be squared. And that should be enough for us to kind of get a rough estimate of what the picture should look like. Alright, so we have 1, 2... Alright, we'll get an idea here. So 1/4 is negative 1. 4 is 1, and then 16 is 2, so it's not going to grow very fast. Alright, so it would look something like this. Now, something that you should remember about the domain of logs is the argument, or the inside part, must be greater than 0. Okay? So, it can't equal 0. There's a vertical asymptote there, so it should never cross that y-axis. And then the range, it goes from negative infinity to positive infinity, so we call that all real numbers. Okay, so now we can combine, hopefully you remember that another way of writing this is ln of x, natural log. So now we're going to use some limits here. If we can't just plug in infinity, alright? In our original function, as x goes towards infinity, this part's going towards infinity. Alright, so the ln of a really big number is going to end up being another really big number. So this one equals infinity. This might help us to get a graph here. So instead of being right here and crossing through, it's moved this means to the right 9. So then our graph is just going to be something like this. So if we approach 9 from the right, it appears that our function is going towards negative infinity. Okay, this one, tangent of x. Alright, if we know our graph of tangent looks like this, and as you approach 1/2 pi from the left, tangent approaches infinity. So if we think about the log as our numbers get really, really big, it's going to approach infinity here. Alright, and then cosine, if we put cosine of 0, we know that that is going to be approaching 1. So we're looking at, for the log as x approaches 1, which would be 0. Alright, so we're using that idea I told you earlier. The inside part must be greater than 0. Hopefully you remember how to solve inequalities. If not, this is a great place to practice. Alright, we can factor this. So we get x minus 2, x minus 1. is greater than 0. And hopefully you remember, if we sketch a quick little number line and put our zeros on here, plug in different values, or compare it to the graph, just to determine which parts are positive and negative. If you put in 0, we're going to get a negative times a negative, or 0, 0. That makes negative times negative should give us a positive number. Okay, if we put in anything between 1 and 2, we should get a negative, and anything greater than 2, we should get a positive. Now we were looking for where it's positive, and then to write that using our notation, it would be from negative infinity to 1, and from 2 to infinity. So that would be the domain of our log function. Alright, these are properties of logs. They're just here for your reference. Hopefully you can use these. Alright, we're going to use the properties to solve the equations for x. Alright, and so for the first one, you just need to rewrite that in exponential form. So the base here, if you don't see a base, you can assume that the base is 10 for a natural log. So it's 10 to the third equals x plus 1. 10 to the third is just 1,000. 1,000 minus 1 is 999. Alright, and just check that. Does it fit in our domain? And it does. Okay, this you can either rewrite using log properties, or if you want to take the ln of both sides, you could do that. Alright, I'll show you that method. Take the ln of both sides. Okay, using our power property, I can move this exponent to the front. And ln of e is just 1. Okay, so I won't have to write that on my next line. And if I subtract 3 from each side, I'll get ln of 14 minus 3. So x, the exact value of x here, would be 3 minus the ln of 14. Alright, this one, if you remember your properties, when you subtract logs with the same base, you can rewrite it as division. Okay, and so doing this, now I can rewrite it into exponential form. So e to the first equals x over x minus 1. And I'm trying to solve for x, so I'm going to multiply both sides by x minus 1. Okay, distribute, I get e times x minus e equals x. Okay, I'm going to move the x, anything with x to the left, and anything without x to the right. So I will get e times x minus x equals e. Only a few more steps here. Factor out an x. So I have e minus 1 left over. And then divide both sides by e minus 1. So x, the exact value of x is e over e minus 1. Okay, last one of this problem. Again, you're using your properties here. If you add two logs with the same base, you can multiply their arguments. So it's log of x times x plus 1 equals log of 6. So here, when I have two logs with the same base equal to each other, I can set the arguments equal to each other. And I'm going to just distribute out this side. X squared plus x equals 6. Move 6 to the other side. X squared plus x minus 6 equals 0. Okay, factor. I can factor this into x plus 3 times x minus 2 equal that to 0. So it appears that x is equal to negative 3. Alright, negative 3, or x equals 2. However, if you tried to plug in negative 3, that would not be in the domain of our function. So we have to discard that answer, and the only answer we have is x equals 2. So there you go. Okay, example 6, find the inverse of the function. Remember that all we did to find the inverse was switch the x and y and solve for y. Alright, so I would have x equals ln of y plus 2. Rewriting this in exponential form, I get e to the x equals y plus 2. Solve, and I get e to the x minus 2 equals y, or my inverse function. So I would say f inverse of x equals e to the x minus 2. Alright, this one looks scary because it's a fraction with exponentials. It's not too bad. So we have x equals 10 to the y over 10 to the y plus 1. Multiply both sides by that denominator. So you get 10 to the y plus 1, all multiplied by x, equals 10 to the y. Alright, so then I'm going to distribute out this side, so I get x times 10 to the y plus x equals 10 to the y. You get anything with a y to one side and everything else to the other. So I'm going to move over my 10 to the y, so x times 10 to the y minus 10 to the y equals negative x. Factor out my 10 to the y here. I get x minus 1. And we're getting closer here, so we get 10 to the y equals x over x minus 1. And so now we have to get that y out of the exponent. One way we could do that is take the natural log of each side, and I would choose the natural log because the base is 10. Alright, so I would take the log of both sides. Okay, and that makes it so that I could move that y to the front, and log base 10 of 10 is just 1. So all that's left on that side is y, and on the right hand side we're going to have log of negative x over x minus 1. And there you go, that's your inverse functions. Alright, so I guess we could do one more example today. Find the point where the tangent line to the curve is perpendicular to this line. Alright, so we know tangent line, we're going to have to find a derivative. So y prime equals e to the negative x times the ln of the base, which is just e in this case, and that turns into 1 times negative 1. So our derivative is simply negative e to the negative x. We need to figure out the slope of this graph, so this would equal 2 times x minus 8 equals y. So our slope is 2. If we want it to be perpendicular, our slope must be negative 1/2. So we need the derivative to equal negative 1/2. So we could just set them equal. So I could multiply both sides by negative 1, or divide by negative 1 to get rid of the negatives. the variable I'm trying to solve for is in the exponent, so I should rewrite this in exponential form, or think about it as taking the ln of both sides. So I get ln of 1/2 equals negative x. And now I just need to solve here. Um, so I can put negative ln of 1/2 equals x. Or another way of writing that, if I put the power up here, okay, that would be ln of 1/2 to the negative 1 power, which would just flip that over. So I get ln of 2 equal to x. And we're trying to find the point where this occurs, so we have to plug it back in. So y equals e to the negative ln of 2. Move the power, so we get e to the ln of 1/2. And since the bases are the same, now I know that that point, the y value at that point, is going to just be 1/2. So our point is ln of 2, 1/2. Alright, so there are a few problems that you could probably accomplish at this point. Some of the beginning ones and some of the multiple choice, I think, involve just ln's without derivatives. We'll get into derivatives with the next video.